That's like it's like then you can literally do anything. That's basically like AR to its fullest capacity. It's a lucid coma. Maybe I don't know. Yeah. If you can do that and slow down your coma at the same time, so that's super slow. Oh yeah, unlimited music. Yeah. And that would be sick. Yeah. It's probably a fucking stupid shit stupid because once we resort to that. Yeah, yeah, yeah. But it's yeah, it's great. Yeah, it's great. So you want to discover, bro? Best concept, not from the bench, not yeah, so now okay, nice.
Okay, yeah, let's get started. So I said I was going to start with a quiz today, but I'm not. I didn't have time to make one, so no quiz today, but maybe Thursday. All right. Okay. We're gonna keep moving, and we're gonna change the order of the class a little bit versus the videos online for anyone following online. Because we're almost done with CUDA for the software side of the class. And what we've done in past semesters is go straight from CUDA into architecture. But I'm gonna instead segue from CUDA into the basics of deep neural networks and focus on, how these map to GPUs. Okay, so we're gonna basically not jump right into hardware. We're probably gonna spend a week on sort of the first part of the machine learning accelerator part of the class, just to give you a sense of like what these algorithms are, and then specifically talk about how they map to GPUs, which will be helpful in your CUDA programming assignment when you're trying to figure out how to do convolution on this thing. I'll make that announcement for the online folks too, and make sure all the videos are available for that particular segment of the class. And then after we sort of finish with deep neural networks and convolutional neural networks and their application to GPUs, we'll move into GPU hardware, and then we'll come back to machine learning specific accelerator hardware at the end of the class. Okay, so to sort of move up the algorithmic piece of machine learning workloads, some of you may know this well already, but not all of you do. So some of this kind of stuff will be review for folks who do work in this space, but for others, new graduate students, this is sort of probably the first time you're ever really seeing this kind of thing. And it's super important, so we should cover it here. But before we move there, I want to cover the last few pieces that we're going to cover in CUDA, at least before we move into the machine learning specific pieces of it. And we're going to talk a little bit more about our shared memory. Okay, so we talked about, how optimizing for shared memory coalescing is sort of like optimization number one from a locality perspective. You have the scratch pad. So when I say shared memory, that's the CUDA terminology. It means the scratch pad. And you don't want to always go to global memory if you've got locality loaded into shared memory and then reuse it. Okay, and then we showed you that piece of code that optimized matrix multiplication, where we did this corner turning thing, right, to try to have nice coalesce accesses from the global memory. Then we loaded it into the shared memory. And then when we did our row column accesses, which were kind of going to be messy if that was from global, we did it on the scratch pad. And we didn't suffer the huge penalty we suffered when we went to the main memory system. Okay, are there any questions on that? On that last piece, we looked at these like little blue squares in the last lecture, right? And then we saw how we sort of accessed it in this sort of row column way from the tile, but the tiles themselves were loaded in contiguous ways. Does that make sense to everybody? Okay. So shared memory is much better than global memory, but you can still screw it up. Okay. In theory, it's as high a bandwidth as your cache, right? Or it's as high a bandwidth as your register file almost. Because in every cycle, you could read out one floating point value from your shared memory, and it's pipelined, And you basically can get a pretty high output out of this thing, but you can screw it up. So let's talk about something known as bank conflicts. Who knows what I'm talking about when I say a bank of memory? Anybody? When I say a bank of memory, what am I talking about? Yeah.
Dividing a large chunk of memory across multiple systems.
Okay. So I'm dividing a large piece of space right across multiple logical chunks. So why would I bank my memory? Why would I want to do this? Yes.
So I think, I don't know exactly, but they have like different pins.
Okay.
So you can read each one parallelly.
Okay. So having more pins in parallel should give you more what? Throughput. Okay. I would bank my memory to give me more throughput on a particular logical piece of memory. What are some other ways I can get more throughput on my memory? Replication. So there's a difference between banking and replication. So if you think about this with respect to an L1 cache, let's say that I've got a superscalar processor, okay, and I want to service 2 loads in one cycle. I could replicate the L1 cache, okay, so they have the exact same data in 2 distinct copies of that cache. And that means I'm basically, like, my storage is effectively the effective capacity is cut in half, right? Because I have to put 1 meg of storage on there and I only get 50 kilobytes worth because I'm replicating the data. But I get double the throughput because I can give back the value to both of those loads in the same cycle. Okay, so that's one way to increase throughput. What's another way? Replication is one. I just replicate my memory structure and then I replicate all the data in that memory structure. But there's a more cell efficient way to do this. Anyone in VLSI? What do I do if I've got a memory structure and I want to service 2 concurrent reads to that same memory structure in the same cycle? What would I do? Yep. Multiple read ports. Okay. So you can always do this, right? You can take any sort of, rectangular memory structure. Ultimately, a read port is a bunch of pins, wires, decode logic that allows you to read out from different places inside that memory. I can add more ports. Okay, what is the problem with adding ports? Area. Okay. Ports are super expensive because there's a lot of extra routing logic that has to happen for you to be able to read out 2 or n things on the same cycle. Okay. So if I am a GPU, okay, and I want to read out, 4 different float values, one different float value for all 32 threads that are in one warp in one cycle. If I do this naively, I would have a 32 port structure, right? Because they all could potentially be accessing different parts of this memory space. That's insane. Like scaling a large memory structure to 32 ports will just explode your area. Your energy efficiency will collapse. Everything scales at a square factor when you start adding ports. So adding ports is sort of, if you're ignoring all the VLSI issues, adding ports is the best solution. Like from an architect, if ports were free, we just port everything because it's like, well, you get the best of both worlds. You don't replicate capacity and you get maximum throughput, okay? So porting is sort of like the ideal architectural way to increase throughput on a memory structure, but it's super expensive and impractical to do at a large scale. Replication is, it scales as it's not squared, right? Because you're just replicating the storage, right? So it's like doubling it every time, but you're wasting capacity. So it's still a waste of area. You're not wasting energy as much because you still only have 1 read port on each of these replicated structures. So it's better from an energy efficiency perspective, but you waste storage. And then the third option, which tries to get rid of both of these problems. So keep your memory structures with 1 single port, but do not replicate the values, is what we call banking. What differentiates banking from replication? Sorry. There's different data in different banks. So when I replicate data on a storage structure, I literally have the same, there's an identical copy. So, it's effectively wasted space to get that extra throughput. In banking, I don't have the same data in each structure. So what am I going to have to do? What do I do to achieve this? How do I ensure that the data is never replicated in these two structures? I'm gonna have the same load instruction, right? From the perspective of the ISA, from the perspective of the core, I'm gonna do one load or maybe two loads, right? And I'm not really gonna see what's going on with these banks. How am I gonna ensure that one of them is gonna go to one bank and one of them is gonna go to another? Yeah.
Change the decoder to, change the address decoder to point to different banks.
Exactly. So I'm gonna spray the address space across the banks in a static way. You could do it dynamically, but it's complex and kind of crazy, okay? So what they do is basically spray the address statically across all of these banks, so that way I get the effect of, essentially, I get the scaling and throughput of a replicated structure because I am, I'm not, everything just has one port, but I don't waste the efficiency of sort of replicating that data. I make sure that every bank has uniquely different data. Okay. What is the most simple way you can think to spray an address space across multiple banks?
Modular.
Sorry, what's that? Over here.
Modular.
A modulo, right? So like I store the first float in the first bank, the second float in the next bank. So address 0, address 4, address 8, address 12, and so on. And that's what we do. Okay, it's a sort of, all other things being equal, unless you have some like disastrous access pattern that always falls on some alignment, you should be evenly accessing all the banks. Okay. So the reason why we do banking is to get throughput, and we need to do it because, this is a high throughput machine. We're going to have multiple reads in one of these shared memory instructions. Now, this is not just applicable to shared memory. Banking happens in all kinds of memory structures. Okay, this is just a concrete example of banking in GPUs. And, if your accesses happen to read all of the banks, then you're golden. Okay, you get throughput and you get it in an area efficient way. If you in the unlucky scenario where your addresses, the things you want in one cycle don't map to different banks, we get something known as a bank conflict. Okay, and that's the problem we're going to review here on this slide. A bank conflict says that, for example, in this, slide, I've got two banks, okay, bank 0 and bank 1. These are two separate memory structures. And in one cycle, I want to read out these two words, let's say, let's call it bytes, whatever. These addresses 0 and 1. And if I've sort of strided it across, and in that same cycle, I want address 0 and I want address 1, then I'm good, right? I read the two out. And banking is more flexible than just a wide memory structure. Okay, so this is the differentiation between like just having a super wide, like think of like doubling the width of a cache line or something, or doubling the width of your read versus banking. So when you bank, you can go to one element in bank and then a different element, not on the same row, like a completely different element, completely different decode on this other bank. And if I do it this way, I also can basically do both of these reads in parallel. Okay, I can process both things in parallel. As long as I read an even and an odd address in the same cycle, I'm good. The problem happens when I try to read two evens or two odds in the same cycle. I am basically not using this memory structure at all. I'm only using, in this example, the even memory structure, which means I'm going to have to do what? I have to serialize it. So now instead of taking one cycle to get my 8 and 2 bytes back, it takes 2 cycles. Okay, this is the nature of a bank conflict, and it's bad because it causes serialization and it effectively reduces your throughput. Because now on this cycle, right, I am at 50% of my maximum throughput from this memory structure because I didn't use half. And whether or not you get bank conflicts is a function of the program and the mapping function. But the mapping functions tend to be static. In CUDA, it is static. They tell you, this is the mapping function, don't screw it up. And then whether or not you get bank conflicts on these loads is a function of what addresses you're touching in the same cycle. Yes?
Bank conflict also affects latency, right?
Yes, so it affects throughput and latency. Again, I tend to focus on throughput because that tends to matter more, but now it's going to take you 2 cycles to clear that one load. So your accesses to a bank structure are not always the same latency, right? Depending on how many elements you need from these structures in one cycle. Yeah,
So there's a read port per bank, right?
correct.
So that means you just typically want to limit how many banks you have in the memory system.
So the more banks you have, the more throughput you have. the more diversity you also have in spraying the address space, right? The less conflicts you tend to have. If you have bazillion banks, right, then, you know, it's better than just having, if you have one bank, it's worst case, you're always going to serialize. I mean, that's just a non-bank structure. If it's two, then you're going to serialize, you know, on a 50% ratio. As you add more banks, the serialization goes down. It's more expensive, right? If I just have a larger single bank structure versus a double bank structure, it still costs me more because I still do have two ports, right? I still have two logical sets of wires that come out of this thing, but I don't have to scale the internal guts of the memory to dual port it. I just have two pins on the outside, okay? And it's way more efficient to do. So it's still costly, but this is the least costly way to scale through. Okay, other questions? You've seen this before. I think we covered in like one slide in 565, right? On how you increase the throughput of a memory structure. Banking, replication, and increasing ports. Okay. Yep.
We can have multiple logical banks on the same physical bank, right?
Multiple logical banks on the same physical bank. I mean, why? What do you mean by that?
So for example, if you partition the address space, then you can have like banks from partition A and banks from partition B share the same physical bank, but you're guaranteed that you never, like, there's no overlap in the memory accesses.
You're kind of conflating two things, I think, right? You're conflating partitions and banks. Ultimately, a bank is just, it is a memory structure. Like this is the lowest level of thing. And if you're trying to go to, you know, it's characterized by some number of ports, right? And if you're trying to go to it with two things in the same cycle that only has one port, then you will still serialize.
Yeah.
Could you, I guess what you're saying is like, could I have some weird structure where I've got like, let's say in a memory system, I have two memory controllers that are logically separating the address space and they somehow share this bank. It's possible, but weird because they will conflict sometimes and you'll get serialization. You're usually better off not doing that and letting a memory controller know what banks it has so it can be better
What I'm
scheduled.
saying is sometimes we can use statistical multiplexing, right?
To share banks across what? So you're talking about changing the address space mapping then? That's effectively like changing the, I think that's what you're suggesting.
Yeah.
That's possible. You could do that, but you know, it's complex and usually you're better off with a good static function. Okay, to try to spray the address space rather than trying to dynamically adapt. Typically, but you know, look, you get into this like space of like data analytics and like this is the access pattern. If I do this particular mapping, it's going to be 10% better for this one, 20% worse for this one. There are, you know, for this shared memory mapping, it's very straightforward. Okay, basically every float in a linear, like every 4 bytes is banked in your shared memory. So that if you access, you know, 32 threads in a warp access 32 parallel floats, you'll get maximum throughput. On the main memory system in NVIDIA GPU, there are crazy like Galois map that goes on to try to figure out how to spray the address space across those partitions because the access patterns are much more diverse than just one shared memory load. So generally, yes, this problem of trying to spray the address space across memory structures gets a lot more complicated. In the shared memory, though, it's pretty straightforward. Okay, other questions? All right. All right, so here is a good access. Okay, so if I'm, this is a write, so reads and writes, so there's one read port, one write. I think it's one read write port, because you would logically only be doing, you know, one operation per cycle here with one instruction. So this is a write to shared memory, where we're just taking, you know, we're indexing A, which we're assuming is stored in shared memory because we declared it that way up here. And then every thread is just accessing the next element of A, and you get this nice linear pattern. Okay. So basically, you know, because there's, and these addresses are actually, these are float addresses, right? So this would be byte address 0, byte address 4, byte address 8, etc. Okay. All right. So a bad access is this, right? If I shove ×2 in there, then now I have a 50% like I basically have a two-way conflict, which means my throughput's cut in half, my latency is doubled. Okay, makes sense? All right. So this is, you know, and this has been true like since the dawn of CUDA, since the dawn of using shared memory, the pattern is set. You can basically, as long as you're always accessing two as long as you're always accessing things that are offset by one float, you will have no conflict. So this is across a whole thread. This is what it would look like. You had sort of a perfect access. If you had this ×2 thing that we just did, what you'd have is, thread 0 attempting to read from bank 0, and then thread 16 is also attempting to read from bank 0. So that's a two-way conflict. So it's going to cause serialization. Broadcast is also possible. So what is this crazy thing doing? Right, actually, this is not broadcast. So this is just saying it actually doesn't matter if it's perfectly interleaved, as long as within any bundle of 32 threads, you're touching all 32 banks, it will work. Okay, so in this example, I'm skipping what? I'm skipping 3 every time, right? So skipping 3 is actually not bad because you're on an odd, right? Because you're going to stride over basically an even, and then if your stride is on an odd pattern, then it'll work out and you won't actually end up with any conflicts. So it doesn't matter whether they're sort of linear like this. That's just the easiest way to think about it. All that matters is in one particular load instruction for a shared memory access, are you touching all the banks or do you have conflicts? Yes.
The stride has to be a prime number, right? For it to have all the.
Does it have to be
conflicts.
prime?
Because if there's 9, if you're.
Yeah, 18. No, eventually if you end up on a 3, 6. Yeah, does it have to be prime? I don't think it has to be prime. It has to be a non-multiple of 32, right? Because if it's 32, then you're screwed, right? And it's a 32-way bank conflict. Well, but 2, it can't be basically. Yeah, I'm pretty sure it's just based on your relation to 32. Yeah.
Wait, so what does the stride mean that we mean this case?
In this crazy case here,
Yeah.
the stride here is 3 floats. So thread 0 touches 0, thread 1 touches 3, thread 2 touches 6, right? So then you're sort of skipping 2 each time. And then when you get down to the bottom, you're going to wrap around, right? So thread 31 is going to touch 29. And then when we, and then, yeah, because you're skipping 3, the actual bottom one, thread 31, is touched by 21, right? Because that's times 7 times 3. Or sorry, what was I talking about? Yeah, because that's the 21st, 21. No, it's not the 21st. Yeah, it is. Is that right? Yeah, that's right. You're just skipping 3 every time. That's it. And then when you get to the bottom and wrap back around, you don't wrap around at the bottom, wrap around at 11, right? Because 10 is going to be 30. And then 11 is going to be 33, but 33 isn't going to wrap back around to 1 because it's a modulo operation. Okay, and then you sort of you happen to then hit the open banks. Yeah.
So this means as long as each thread accesses a particular bank, we don't have an issue.
Yeah, that's correct.
No failure.
Correct. There's no serial. As long as every thread accesses its own bank, there's no serialization.
So that is it can be any arbitrary bank.
Yeah, that's correct. You could have some weird, you could do an indirect access, right? Where you've got, where every thread reads from an array that is just completely randomized which thread does what. And as long as every thread is accessing a different bank, you have no bank conflicts. Okay. Other questions? These ones are harder to pick up, right? They're a little bit less intuitive than the sort of linear thing, but you can measure this at runtime to see what you're like. If you have some weird dynamic access, the profile will tell you how many bank conflicts you have on every shared memory access when you're trying to optimize these things, if it becomes less obvious. Okay. Other questions? Okay. The other thing, I don't know, I didn't mention it here, but broadcast is possible. So if they all access the same bank and they access the same value in said bank, then there's also no bank conflicts. Same is true for, if half of them access bank 0, but they all access element 0, and the other half access bank 16, and they all access element 1 in bank 16, then, then there's no conflict because you can feed all of the threads in a broadcast map. Okay, so it's only when you access different values in the same bank that you end up with this serialization. Okay. All right, so let's take a look at a pretty simple kernel that's just going to do matrix transpose. Okay, so if we did matrix transpose, so the idea is, right, you've got some input data, and if you're reading from sort of a block of this data, you want to read in the row, and then basically you're going to take the column and then make the column the row. That's the idea behind the transpose. Okay, so in this example, we have this 2x2 matrix. The input data looks like this. I want to read in, I basically take this, what am I talking about here? Right, so this is the input, right? I want it to take this row and then it ends up having to be transposed into this column, right? That is the nature of a transpose operation. So the way that we do this is read a block from data into shared memory. So read this entire row in. So do you think that this access is going to be good or bad if I'm doing this across parallel threads? Any guesses? It's a binary decision. If I am having if I have a 2-thread system, right, and I have thread 1 access this element and thread 2 access this element, is this going to be good or bad for memory coalescing?
Bad.
Wrong. Good. This is going to be good, right? Because they're both going to pull them in. They're going to load them into the shared memory and sort of this. Remember, everything's row major, right? So it's going to be contiguous addresses. Okay. So I copy it into the shared memory. So now I've got my block happily living here in shared memory. So now when I read out of shared memory, okay, I'm going to want to read out the column and then write it out to the memory space. And then for this particular access, do you think this is going to be good or bad? If again, I have thread 1 and 2 doing a sort of 1-3 here, it's going to be good, right? So I use shared memory here to essentially perform corner turning. The naive solution is not use shared memory, load it all in and then spray it all out, right? So have it, like if you have a thread, every thread loads a contiguous piece of the row into their private registers, and then they spray out that contiguous piece that they loaded into the registers to where it needs to go. But unfortunately, if we look at where the register capacity is, right? So if I just did it without shared memory, I would have loaded 1, 2 into my private registers. And then when I stored it out, I'd store it out like this. And this is not good, right? Because now my store is separated by an entire row matrix, which is bad news. Okay, and this toy example obviously is not a huge problem because it's so small. But generally, the way that we want to optimize transpose for memory coalescing is to do this. Load it in a contiguous way. And then when we read from the shared memory, we read it in this column-wise way because it's not costly to read column-wise from the shared memory. And then when we write it out in this contiguous way. Okay, with me so far? So this is an optimization I did on transpose to try to avoid the coalescing disaster that you would have if you didn't use shared memory. So this is sort of the first level optimization. If you don't do this, transpose is a disaster, right? Because it's like every store is just a scatter. Or if you tried to make every store contiguous, every load is a scatter. And either way, it's bad. Okay, so your bandwidth is crap. So to do this, the kernel would look like this. Okay, so this is just a very simple coalesce transposed kernel. We do the same kind of, computations. We're assuming that this is sort of a 2D thing, right? Because we're doing a matrix. You guys have seen this multiple times before. First part of this is just taking a block of shared memory, creating all of our particular indices to sort of do what I showed you on the last slide. And then we have a little loop in here where we're loading into this shared memory tile. Okay, so this is where we load everything into shared memory. And it's going to happen in a sort of nice contiguous way based on these accesses. Okay, so the I data is going to be read in a nice contiguous way. And then it's stored in the tile. We do async threads here because this is a cooperative load. We're bringing everything into shared memory. And then, the core reason is, every thread was going to load a piece of this little matrix into their register space, but you're not going to only use the things you loaded. You're also going to use the things other people loaded in the shared memory. So you have to wait for them to complete. Once we're done, we go ahead and we write out. So this is the output where we put our nice coalesced write to the memory system. And we read from the shared memory tile in that sort of column-wise way, but that's not really a big deal because we're not going to have this weird scatter, okay? Questions on this? So this is like a very small example of corner turning where I am loading something contiguously from the global memory, putting it in my scratch pad, accessing the scratch pad in a way that would have been disastrous to access from the global memory, and then sort of spraying it back out to the global memory in a very nice pattern. Okay. So there are no coalescing problems with this workload. I've skipped the like naive one where you don't put it in shared memory first, because that'd be a disaster for coalescing. Questions on this? And you guys should have enough context to sort of figure out like why these loads are okay, right? So for example, this load to iData, you can figure out, well, is this thing actually going to be, you know, a nice load? So let's look at all the terms inside the pattern, inside the index computation. So is I going to be constant across all the threads in a warp? This is a good exercise, actually, because maybe you guys don't get this yet. Let's evaluate every term in this iData load. This is a load. This will boil down to a load to global memory. And the way that I need to think about this from a coalescing perspective is what happens to every variable across the warp, okay? The I variable. Across a warp, is that going to be different? Is it going to change in, you know, a predictable way? What do you think? Yep.
It will be the same across the threads in a warp.
It should be the same across the threads in a warp. Why?
Because they're all like going through the for loop together.
That's right. So everyone is going through this for loop together. Okay. This lockstep execution. So all of the threads start out with I equals 0. Like this gets stored in their private thread registers. By the time they get in here in the first iteration, I is 0 for everybody. Okay. And then the first iteration, I is 0, so this term goes away. All right, so then I got to look at what is index in. So I come back up here and I look at this thing. So this is index in. So then it's composed of this weird thing where you've got, you know, X index. So this is how X index gets computed. And then Y index based on, you know, where in the block it lives, right? Or where in the sort of grid it lives, because this is a two-dimensional thing. So in the simple case, let's assume that Y is 0. Okay, so this thing goes away. And all we're left with is X index, right? And is this X index a good pattern or a bad pattern for coalescing? It's a good pattern, right? It follows this formula that I basically told you last time, where you've got some kind of math that is not dependent on TIDX. Because remember, TIDX changes in between threads in the same warp. It's the fastest changing dimension. And then you're just adding TIDX.x, which means that consecutive threads in a warp are going to access consecutive addresses. So on that very first load, I equals 0, when we're looking at Y index 0, you're going to have a nice coalesced load. Now, depending on the size of your tiles, this may not be perfectly coalesced, because if your tile is smaller than the warp, the width is smaller than the warp, then you may end up with 2 accesses instead of 1. But you're not like accessing it in sort of a terrible way. Okay. So you should be able to reason about this. And I think we have quizzes on this kind of nonsense, right? Like how to, not nonsense. When you're optimizing CUDA programs, okay. So when you optimize CUDA programs, what you should do both a theoretical and an empirical analysis. All right. You should have the ability to look at some code and know whether this thing is going to be bad or not. But you can also just run the profiler, right? And then it'll tell you that, oh, this is your problem, right? Never discount either of those two paths, right? Make sure that you can do it in your head, do the thought exercise, but then measure it. Right, and the profiler would tell you that, oh, this was bad, because if it tells you it's bad, you need to then go figure out why, right? And if you're just like, I have no idea why it's bad, but it is, then you can't fix it. Okay. So this is sort of a nice coalesced access that's doing a load, and then the same thing is true if you did the analysis on O data, which is the store to the global memory system. That's also nice and coalesced. Okay, questions on this? All right. What do you think some problems could be here? Yes or no? So I got this to work to get rid of memory coalescing. Let's assume that's no longer a problem. What problem might be in this code?
when they're accessing the shared memory block,
Mhm.
if the tile width isn't properly sized, then they're gonna have bank conflicts.
Yep, very good. You should have been hit when I talked about for the last 20 minutes, right? I didn't talk about bank conflicts to just ignore them. So we did the optimization to get coalescing to work well. But I could end up, depending on what my tile width is, right? Because if you look at the size of our tile here, it's dependent on your tile width. If your tile width falls on some poor boundary, okay, some poor power of two boundary, really any power of two boundary, you're going to end up accessing from the same load instruction or the same store instruction, the same bank, which is going to result in bank conflicts and shared memory serialization. Now, when you look at this and you say, okay, how big of a problem is this? It's a secondary optimization problem. Okay, having the uncoalesced write to global memory will cost you like, 8-9 times performance. Having the poor bank conflicts will cost you 20-30% performance. Okay, so this is like the second level optimization that you want to do on a CUDA program. So you don't usually worry about bank conflicts until you first dealt with your main memory system, because if the main memory is screwed up, that dominates the execution time. Okay, but it's still a problem, right? If you're tuning kernels and you've got this big GPU, losing 20-30% of your efficiency because your code has just got bank conflicts is bad news. Okay, so optimized kernels will consider this. Okay, so let's see, let's go back to this thing, right? So basically this is good. Okay, this is a good, so we're going to focus on this one line of the program. We intentionally created a good coalesced write to the memory system, but in the process, we are going to create shared memory bank conflicts if we have nice power of two dimensions for our tile width, which we probably will, right? Because who makes like 3x3 tiles? It's weird, because it's directly going to be, the tile width is the same as your block width, right? So they tend to be powers of 2, 256, 512 total size, etc. So when we do that, we're going to end up with these conflicting patterns. Okay, so in sort of pictorially, what does that look like? So the problem here is this one. The problem here is this access to the columns from the shared memory system. Now, we can fix this, and we can actually fix it incredibly simply. Okay, it's not actually a huge fix or a huge change to the code to avoid this pathological sort of, you can think of this as like a pathological stride. What do we need to do ultimately? What do we need to do to avoid the sort of disastrous bank conflicts that we see here? Add an offset to what? To the read from shared memory? Okay, if we do that, we're not going to get the right data.
Even when writing.
Even when writing, okay. So add an offset. Okay. Okay, so add padding. Yes, so the answer is padding. But do I need to change any of my indexes if I add padding? My index logic in that code. So does everyone know what padding is? Okay, what is padding? Somebody other than the person who answered the question. What does padding mean? Yeah. You want to answer, I can tell.
Like adding like a blink horizon to get everything to align them.
Right. So basically adding data, adding storage that is by definition going to be empty. Like you're never going to use it, but you're going to allocate it. What is an example of padding that you've seen before this class? Sorry, I heard a whisper. Structs? Did somebody say structs? How are structs padded? Basic C. Okay, this is like 264, hopefully teaches you this. Maybe not. How are structs padded?
They can just add 0. They basically add zeros like to get add zeros to get everything to align, or
Okay, align to what?
align to a word.
No. Forgive my syntax, okay? If I do size of on an A, what am I gonna get back? 9? Well, I'm gonna get back 16. Why?
X plus 7.
Because it pads. Because all structures in C must be self-aligned. Meaning that if my compiler does this for me, right? You never thought, I really hope somebody showed you this before, right? You know this happens, I hope, right? But generally programmers, computer science people probably don't think about this. I don't know, right? You don't think about this, but it's happening. Because if I declared a struct, why do you think it does this? So let me tell you what it does for those of you who don't remember, right? So it looks at all of the data types in the structure, and then it makes sure that the size of the structure is a multiple of the largest data type. Okay? So in this example, my largest data type is 8 bytes because it's a double. Then I have this bool that's 1 byte. So if I lay out a struct in memory, I would have essentially a 9-byte structure, which is doable, but it's bad for what reasons? Alignment. In particular, when I do what with an A structure? What do I usually do with a struct? I make an array of it, right? If I make an array of A, right, and I just want to, and the way the compiler does it is it knows the size of every, thing in your array and then offsets it to get the next index. So if I had an array of A's and I wanted to go to A at 1 and I didn't add a pad, then I'd be accessing address 9. If it started at 0, I would go to address 9. For any of you who've done any kind of like low-level ISA, you really do not want to load from a double on a 9-aligned address, right? That is going to require 2 memory accesses. Some ISAs just puke and die, tell you can't do it, right? So as a result, C just says, all right, look, like machines like aligned addresses. So I'm going to always make sure that all structs are self-aligned, and I've got to pad the struct every time. So every time I allocate, if I did a new A or I declared A inside my stack somehow, it's going to allocate 16 bytes for that thing because it adds 3 extra bytes of padding. Sorry, not 3. It's 15 extra bytes of padding here, for after the A variable in the struct. And that is never used, right? It is by definition just essentially empty. You can write, if you're like, I want to be cool, I can do this. Okay, I can do char, temp 15. Well, this is crappy, but envision this line is here. I can do char T15 in this structure to explicitly say that I want it padded, and it compiles to exactly the same thing, except now you could potentially reference that data. I mean, you could still reference the data if you do crazy pointer math, like just find the address of A and then go +1, like it's in there, right? But you don't usually do that when you're like writing nice code. So, all right, why did I do this? This is an example of padding. Padding is explicitly adding basically unused values to structures for some good. We do it in C because we want to make sure that structures are self-aligned so that we don't end up with these weird memory accesses that are all out of whack with the alignment of the data type and bad for machines. In this example, we're going to add padding to fix the problem. Where do you think we're going to add padding? It has nothing to do with structs. I just like talking about C. So think about what causes the problem. What is the data structure here that's causing? What is the variable that causes the problem? Yep. Little a. No, not here.
Oh, yeah.
We're off of that now. Come on, man. There. All right. What is the data structure in what is the variable in this very simple piece of code that causes our conflict problem? Yep.
TIDX.
TIDX? Nope, it's not TIDX. Yep.
Tile variable?
The tile. Tile is the problem. Okay, that's the shared memory object. And the problem with tile is that tile dim is probably 8, 16, 32. Right? Because when you make your thread blocks, this is what we told you to do, right? Because you want it all to be some multiple of 32, so you have like good warps, etc. I'm not telling you to not do that. That would be stupid. You'd lose efficiency in other areas. But because tile dim is a power of, is going to be, a power of 2, and if we are sort of spraying things across the bank so that it's like 0, 1, 2, 3, et cetera, all the way up to 32, that means that, you know, this will lay out data like this, right, in shared memory logically, which means that one row will, you know, will be the size of whatever tile dimension is, okay? And so if I have, you know, adjacent, basically it'll end up that you have this weird sort of, you know, you're off. If it's 32 is just a sort of easy example. So every time I want to access, right, the problem is this, right, tidx.x. So I'm trying to select here among parallel threads in the same warp, which row of this structure I'm going to access. And the offset of those rows is going to be some power of 2, which means that the address is then going to be a power of 2 when I go compute them, okay? Which means that it's going to fall on this weird pathological stride. So for example, let's say that we had 0, right? Let's say that we're talking about the 0th y. And then I looked at, you know, my shared memory structure. And so what this says is I want to access row 0 and let's say row 16, right? Row 32, et cetera. These are the addresses that I'm going to get in my shared memory. These are going to wrap around and have, what is the conflict rate if my block size is, if my tile dimension is 16? How many conflicts will I get on every access to shared memory at tile dim 16 in this case? Yeah. No. 16. Tile dim is 32. How many conflicts am I going to get? 32. Okay. The number of conflicts you get is directly relational to the size of that tile. And you're going to, by necessity, make it some power of 2. And you don't want to start sizing your thread tiles based on memory bank conflicts because you already did all the work to figure out how big I was supposed to make it for occupancy, et cetera. So I don't want to change tile dimension, okay, just to fix shared memory bank conflicts. So what am I going to do if I don't change tile dim? Yep.
So then you add padding to get them all on different banks then?
Right. Where would I add the padding?
Add them between each elements?
Yep. Well, every element. So if I added one extra dead space to every float, so I have float, dead space, float, dead space, float, dead space. That doesn't help. It's still even, right? Every row. So if I add dead space to every row, my code looks like this. Okay, I just add 1, right? So now instead of having every row be some pathological power of 2, every row is now some odd number. So if my threads are accessing, you know, if my threads are accessing, like, let's say the tile width is 32. Let's take that toy example, right? So tile width is 32. That was a disaster in the original case. But now, if my block, so I still have, you know, 32 floats of good data, and then I've got 1 float of like data I don't care about, but that means that the next, so the sort of top left element is address 0, right, in the memory space. What is the address of the next element? 33, right, if I'm assuming I have a 32 wide tile, okay? So the next element is 33, and then the next element is, you know, 33 plus another 33, right? So 66. And then if I mod 32 on these things, right, I end up with 1, I end up with 2. And now all of a sudden, instead of always, I had this disastrous 32-way conflict. So the throughput of my shared memory and the throughput of all my ALUs is cut to a 32nd of what it should be. Just by offsetting the size of this array so that way they're not all clashing on the same bank, I've now got 100% throughput. Okay, because they're all accessing different banks because they're going to get offset by, because essentially you made your array that's not power to crazy size. So the address that you want for each of these elements is going to be non-power of 2. And actually in this case, it's going to be, you know, perfectly no complex. Okay. And that's it. So the code I showed you versus the code here, this code is, I haven't measured it lately, but I think it's like twice as fast maybe, because you've gotten rid of all the bank conflicts. Yep.
Will this change? It won't change anything else in the action pattern of how we load the data.
That's right. Yeah, it changes nothing because I'm still using, like, let's take 32 as a tile dimension. I'm still using a nice wide 32 tile, right? And I'm loading that nice wide 32 tile into my shared memory. But now I've got this extra element on each end that just sits there unused. Okay, what is the downside of this? This wasn't free, yeah.
You're wasting shared.
You're wasting shared memory. This is precious on chip scratchpad resource and wasting it. But unless you actually could pack more work in with that small amount of waste, this is a net win. Okay. Questions on this? Yeah.
Is there a way to make this obvious? Like if someone new were to come into the school, like, why is this like what is this +1 doing here? Let me just get rid of it because it's like wasting shared memory, right?
Yep.
And then, like then they don't realize that it's until after the fact that it's like affecting performance.
Yep.
Is there like good programming practice like items here besides like I guess simple comments?
So I thought for shared memory bank conflicts especially, you usually want to profile it, right? You want to like, you have to run it and see where your conflicts are, right? Have you heard this term, premature optimization is the root of all evil? This is like a software engineering term, right? And us in the systems, area, we all sort of suffer from this is that like, oh, we know something is inefficient, so we're going to go fix it. But you have to measure how inefficient it is before you go off and do it, right? So in this particular example, yeah, like let's say you're an intern, okay, and then they hire you and they like, oh, look, here's our transpose kernel. Can you try and squeeze some performance out of it? And you're like, what idiot put +1 in here? This is wasting shared memory. And you take it out, as you would, right? You don't go back to your manager and say, oh, look, I saved your shared memory. You'd run it and you'd be like, uh-oh. What? Why? This is like, if you don't understand bank complex, this looks like magic, right? This is like, oh, I took out my printf and my code works, right? This is like, to a naive software developer, this doesn't seem like it matters, but to CUDA developers, this does matter. So I guess your question is like, you have to measure it, right? Yeah. At the end of the day, the only way to really figure out what the problem is to measure things. And especially, you also have to do some like mind jujitsu to figure out like what's going on here based on these sizes, right? To try to figure out the patterns. You don't always have to start there. You could start with the profile and see like, and it'll tell you, oh, and the profilers now are actually really good. Like I think it'll even just tell you like, this is the #1 problem with your program, shared memory bank complex. And it'll tell you what line of the program it's on, right? And you just go look. And then you can be like, well, I don't know. Right. And I guess if you're a naive intern, you took away the +1. Yeah, that's what you would do. You'd be like, so you measure it, you took away the +1, you could go back to your manager and say, I don't know why, but like this thing shared memory bank complex goes away when I add this +1, so I'm just going to leave it here. I've shipped code at EA where we left printfs in there because an engineer was like, I don't know if I take it away, it crashes. There's always a reason, right? The compiler was doing something different when the printf was in there that caused your crappy code to not crash, and you just got away with it. But there's always a reason. Okay. I don't know if that answers your question. But yeah. All right. Other questions? All right. Okay, so logically it looks like this, right? If we go back to our toy example, that's 2 by 2. So now we've got this dead space in here. And when we loaded the data, because because we're using this 2-dimensional array thing, right? You ended up just without changing any indices, just by changing the size of the shared memory data structure, you naturally created this sort of, dead space where you basically ended up on one particular. Like if this is bank 0 and this is bank 1 of your shared memory, on one particular load to that shared memory, you're offset by 1. So you're not going to get a bank conflict and you're still writing things out in a nice coalesced way. So in this way, we've gotten rid of both the problem with coalescing and we got rid of the problem with bank conflicts. Okay. Questions? And this is the easiest example of bank conflicts, right? Very sort of toy kernel, but like when you use shared memory, you're gonna end up with bank conflicts. Really, it's the degree to which your bank conflicts is killing you that you end up having to choose. Yeah.
That was mainly my question was like, what are other like common things where you don't eliminate bank conflicts because it actually decreases performance?
So if this pad resulted in, you not getting a whole nother thread block on the core because you don't have enough shared memory, then there'd be a trade-off between like, okay, I lose all my concurrency if I add this pad. But, if I have all the concurrency, they're all running worse, right? So there are examples where these kind of strange trade-offs where losing something in one place will gain in another would have to be evaluated. And again, this should be driven by profiling, but you should know why it's happening and know the fix for it. Okay, does that answer? Other question? Yeah.
The tile dimension changes, it
Yeah.
also changed the padding that we have to do, right?
Yeah, potentially. Because you'll end up with, you just want to make sure, you have to just do the math of like, depending on what your tile dimension is, what would you need to add as the pad? In this example, I did the sort of worst case 32 way. If it was 8, would +1 still work? I think it still works because it still offsets all of them by +1 as you go. So, but if you had some other non-power of 2 thing, you would need to change it. But typically you won't. You usually don't have tile widths that are not power of 2. Okay. Other questions? Yep.
Is there a way like we can mention that this variable should be placed in this particular hardware address of the standard?
This variable should be in this particular hardware address of the shared memory. No, you can't. Well, I mean, I think you can, right? If you just, with casting, I can call a shared memory pointer wherever I like, right? So I could basically, I think compiler will accept this. It's kind of nasty. I don't know, you don't generally want to do this, but you could, like, you could declare a shared memory star, right? And then pass just a hard-coded address to like my favorite place in shared memory I want this thing to live. And the compiler shouldn't complain. And then you can effectively place every variable in shared memory in every place that you would like. That sounds like nasty code to maintain and read, but it's feasible. Usually these kinds of tricks like padding are enough. You don't need to like have some map of like map the shared memory in this way if my dimensions are this way or whatever. But you could, right? It's just software. You could cast it around and get it nasty looking if you want it. Other questions? Yep.
Wait, so the definition of this then is that you have 1, 2, and you have 1, 2, then 4, and 3 are all in different banks.
Mm-hmm. Yep. Because there's this dead space. Because this is 2 by 2. This is just like a trivial example. But because there's dead space, 1 and 3, which is what you're going to read on the what you read from shared memory when you write out the O data. Those are in different banks. And then 3 and 4, which is what you, 2 and 4, which is what you read when you do the second row, those are in different banks. Okay. Other questions? And this is not a GPU thing, okay? This is just a banking thing, right? Whenever you've got a memory structure and you have these weird pathological strides, it's really just an address spraying thing that causes these problems. Okay. All right, yeah, final point here on the shared memory is that it can broadcast. So if you're accessing the same data element from multiple threads, it's not a conflict as long as it's the exact same float. Then it'll broadcast the data out. So there's no conflict in any of these pieces of code, for example. Okay. I think this is a quiz question. Oh, damn it, I gave you the answer. So, you should sort of self-test yourself on this. And I think the video maybe goes over the answer here. It depends. It ends up depending on the tile width, but you should sort of prove that to yourself. Okay, so shared memory. So shared memory used to be way more performant than the L1 cache. So there's on-chip scratchpad on these things. Shared memory was sort of the way you were supposed to use it. And the L1 cache was a joke, right? It was low bandwidth. It was relatively small. And it mostly was just a coalescing buffer. It usually didn't end up in sort of temporal hits across warps. And this is Pascal architecture. So this was, circa 8 years ago or so. And then they changed it. So they were two separate structures. Actually, in Pascal, they bolted the L1 cache onto the texture cache, okay, which we'll talk about when we talk about rendering. And some machines still do this. They have the L1 cache, the L1 data cache share the SRAM with their texturing system. But in modern machines, they've merged the L1 and the shared memory together. We've mentioned this in passing before. So they're sharing one collection of SRAM, and the throughput of the L1 cache is now much higher. So they've increased the tag throughput on the L1 to try to make it more competitive with shared memory. In the early days, the tag throughput on the L1 cache was just 1 per cycle, which meant that you could not keep up. Like even if you had a good access pattern and you were trying to use the L1 cache to manage that access pattern, it would not be as performant as the shared memory. Today, that's less true, but it's still sort of true. And this shared space is basically the machine will decide how to partition this based on your kernel. So if your stupid kernels that you wrote that had no shared memory, they will use all of the on-chip SRAM or at least all the on-chip SRAM that's shared for the L1. It'll just make your L1 as big as it can with the space. And if your kernel is using shared memory, then when you launch the kernel, the SM will get programmed to subdivide in a static way the L1 cache with your shared memory based on the demand of the shared memory. Okay, so whatever is left over will be your L1 cache, essentially. Right, and so the innovations, and this is true today, even in the Hopper architecture, they have this claim that you can have unlimited cache misses. Okay, so this thing called a streaming cache is what they call it, and the L1 cache essentially allows you to miss infinitely, which, there's always asterisks on this. Basically, you can miss enough to saturate your interconnect bandwidth or your L2 bandwidth. That's the bottom line there. How do they implement this? It's probably just a boatload of MSHRs that ensure that you can have many, many outstanding misses in play. Since it's not bolted to the texturing cache, it's bolted to the shared memory, it's relatively fast, low latency hit time. And it's got 4 times the bandwidth than sort of the ones when they had it on the texture cache, because it can check 4 tags at once, and it's much bigger. And shared memory is sort of partitioned between the L1 and whatever you declare for shared memory. If you use the shared memory well, you're usually better off using the shared memory as opposed to the L1 cache. But it costs, you have to tune it, right? You have to figure out how much to use, so you get a bunch of the performance without even using the shared memory in modern machines, but it's still better. So for example, if you sort of have the same access pattern in sort of older chips, and you did it in the shared memory versus doing it in the L1 cache, you'd only get about 70%, or sorry, you did it in the L1 cache versus the shared memory, you'd only get about 70% of the performance. Now, in modern machines, you only lose something like 5 to 10% of the performance by using the L1 cache, if the access pattern is amenable, and if you aren't if your scheduling isn't just destroying things. So if you sort of paste them at the same rate with the same threads and that kind of thing. So usually you have to structure your program to use the scratch pad, the shared memory, and we still encourage people to do this. But the cache is easier to use. And in particular, it's sort of like trying to find, the parts of your code that matter most, right? You code up your program, you don't use your shared memory, you figure out where the bottlenecks are, and then pick and choose which parts of your code you want to optimize for the shared memory, and the cache will sort of handle the rest. Other things that the shared memory has versus the cache is that it has fast atomics. So you can do atomic operations that are visible among all of the threads within a thread block. You can use more of the banks because, when they say more banks, that basically means they don't have the tag throughput in the L1 to keep up with the bank throughput of the shared memory, and it's more predictable. If you guarantee that you have no bank conflicts, then you will get, you'll be able to read every cycle all 128 bytes out of the shared memory scratch pad, because the data is in there. The L1 cache is less predictable because there's scheduling intricacies that screw it up, right? That schedule, you may end up having stuff kicked out of your cache that you thought was there. So shared memory is still the way to go if you really want peak performance. Okay, that's it. Any other questions on shared memory? So those are the basics of using it. You need to size it correctly for occupancy, and then once it's sized correctly, you need to make sure you don't have conflicts in the shared memory structure. All right. Okay, we'll cover a couple of other sort of cleanup items here, hopefully quickly. So streams, who has heard of streams before in GPUs? You have, haven't you? Yeah. Okay. Yeah, and no one else knows what a stream is? All right, so what is a stream? So you guys are launching kernels. Okay, that's, you wrote CUDA code already, or you are writing, hopefully done. That spawns kernels. When you spawn kernels, what happens is it's asynchronous, right? So you spawn the kernel and then it goes into a FIFO. And then the kernels are ordered. So the kernels are processed in order. Okay, this is fine if you have big kernels that use the whole machine, right? Because like you basically have this FIFO of all the kernels that you've launched, and then the system will start to drain the FIFO by running each of those kernels in order. Okay, it's an in order queue. But you may not always have that. You may have like 10 kernels that you want to launch, none of which will use the entire GPU, but you want them to run at the same time. You can't just spawn them in this usual way that we've been spawning them, because the machine will enforce an order when you spawn things sort of with the default mechanism. If you don't care about the order in which your kernels are completed or begin, then you can use streams, okay? You can also control the order with streams, but the basic idea is that if I had two little kernels, let's say, that fill the whole GPU, and I wanted them to run at the same time, I would spawn them in two different streams, and the system would allow them to run at the same time, and they would fill the GPU as best it could. Now, there are limits on the number of streams you can have, but that's the basic idea. And most optimized workloads, like if you look at machine learning workloads, et cetera, they will use streams to try to overlap the execution of independent kernels when there's enough space on the GPU. Okay. Questions so far? So there's a construct in CUDA called a stream that allows you to do this. So here's an example of one way you could use streams. So you can use this to help hide the memory latency, the memory copy latency of a big kernel. So this is, so I had this sort of example of like, I wanted to run two kernels at once. Another way that you can use the streams is to break up a big kernel into smaller kernels. And you can then sort of overlap the memory copy of pieces of that big kernel with pieces of the compute of that same kernel. So in this example, I had this giant kernel, and if you are launching it and sort of doing it in the way that we've done so far in class, you are not using the GPU here and here because you're in memcopy town. Okay, memcopies take a long time, especially if it's a big amount of data, and your GPU is not doing anything. You could break up that big kernel into three little kernels, each of which has a little memory copy, and then you could essentially just pipeline this thing, right? You can basically say, I want kernels. So in one stream, I'm going to spawn kernel 0, and then I'm also going to spawn the CUDA memcopy for that, kernel 0, which K0 is logically just this first part of this big kernel. K1 is the other part, right? And then K2 is the last part. And then I can spawn K1 and K2 in their own streams, and then I can overlap the execution of the kernel with the memory copy. So I ended up saving time, right? Because I'm overlapping the memory transfers with the kernel. Okay, that's sort of that's the reason why they invented streams in the first place. Questions on this? Yep.
So in this case, do these will they be mapped on different SMs? Because otherwise there's shared memory.
Yeah, good question. So in the early days, yes, you could only map. So every SM will be assigned to a particular kernel, because there are complications if you don't do that, right? Because think about shared memory, right? Like how it's a lot easier to schedule things if you know that every block has the same resource demands. If I'm going to put two kernels on the same SM, they will have different resource demands. Now I can't just use a very simplistic allocation mechanism. I need something that's more nuanced. So in the latest machines, like the Hopper machines, I think even in the Volta machines, they do allow for multiple kernels on the same SM, and they sort of handle that complexity. You can force it not to do this too if you don't want it. But yeah, so again, it's a hardware feature. It's present in modern machines. It wasn't there in the beginning. Good question. Other questions? But you're right in that it makes things trickier, because now I end up, you can have essentially interference, right? The way that they do it, actually, I don't know precisely how they do it. If it's just a plain static partitioning where if there's two types, they get half the resources, or if they try to match it based on thread blocks, there's some heuristics that they try to do there. Generally, you can be aggressive like that, but I think that it's usually better to just give whole SMs to whole kernels, typically. Okay, other questions? All right. So this is how you write this thing. You have to declare these like stream structures, and you have to create the streams. And then this is just an example of like a loop where I'm spawning 3 different kernels. You have to use this like async memcopy. Okay, so you don't use the normal memcopies because the normal memcopies will always go into what they call the default stream, which is stream 0. If you want to do this overlapping and put things in different streams, you have to use this async memcopy, which means it's non-blocking. It puts it in the stream. So you dump async memcopy in, you dump the kernel spawn in, and then you dump the async memcopy back. And then in all of these, you have to pass some handle to tell it what stream you're using. Okay. And this is sort of the API you have to use if you want to use streams. Streams used to be really stupid because there were no hardware queues. There were no distributed hardware queues. So if I had 3 logical streams that that had 3 logical pieces like A, B, and C, each of which were in a different stream, ultimately the hardware would end up serializing, so you couldn't actually get overlapping between kernels. You couldn't get full overlapping between kernels. This, I don't even know if I want to belabor this slide anymore because this is just dead, right? So they had this thing called hyperqueue that they invented, which is basically just multiple hardware queues. So that way, when you push into the streams, you are actually pushing into a different logical hardware queue. The downside here is that streams are a software thing, so you can create 1,000 streams if you want, but you only have a finite number of hardware queues to allow the overlapping execution. I think in modern machines it's like 128 or something, so it's pretty big. But it basically allows you to overlap the execution of kernels on different streams, provided that there's enough in the GPU. Okay. Generally, the kernel scheduler is greedy, so the only way you could get 2 different kernels running on the same GPU is if one kernel didn't use the whole thing. Okay, it's sort of a sticky scheduler. So it says, I'm going to schedule all the thread blocks from this kernel. And then once that runs out of thread blocks, it'll switch to the next kernel. But it won't be like, I'm going to take 1 thread block from this guy and 1 thread block from this guy. Generally, that's not optimal for throughput, so it doesn't do that. So the only way you would get this scenario where there's 32 or whatever different kernels running at the same time is if each of those kernels was small and we could actually fit them all in space in the GPU at the same time. Questions? I'm going to end there. We'll come back and just cover up these last 2 things quickly next lecture. I posted the slides for the next probably the next 2 weeks already to Piazza. So please do take a look if you want to take a look at the slides in advance. And I also will not have office hours this week at my usual time. If you do want to come talk to me, send me an email. We'll do it on demand. We're doing interviews for new faculty candidates this week, so I have conflicts with my current time. Okay, thank you all, and we'll see you on Thursday.